Hey everyone, and welcome to our weekly live stream of coding the emulator for Raspberry Pi Pico. First of all, I'm really happy to see we have Nekati and Valerio here in the chat. Valerio is saying that it's better than Netflix. I'm glad. And it's also a good opportunity to give a shout out to Valerio for doing such great work finding bugs in the emulator and improving our tooling, and I will show you that in a moment. So first of all, as usual, let me know in the chat if the audio and the visuals are fine, and let me share the screen. So before I don't even know why I have this open. I haven't really touched this since the last spontaneous stream on Saturday, or was that Friday? Yes. Before we dive in, just one more word. Me and my family are, thanks God, fine, and there is still war going here in Israel, and I hope we won't be interrupted this time. The situation is still not very good, but we will try to do our best to we're trying our best to stay optimistic and keep going on with life. And so we hope this stream will go without any special alerts and so on. Anyway, let's go back to I'm not sure if everybody has watched all these 4 spontaneous streams since we had the last episode 2 weeks ago. So we are going to go real quick, like 5 minutes. I'm checking myself with a clock. 5 minutes just to get a real quick high-level overview of what happened in those streams. So going back in the commit history, and yeah, that was our last episode 14 days ago, where we started working on Systic and basically fixed a bunch of bugs. As I can see here, not really added. Yeah, Systic is like a new feature. And then Valerio did this change, which is not really, I don't think it should change anything in the logic. It just makes the code easier to understand. And then in the next spontaneous live stream, you can see we added a bunch of like all the instructions that we still didn't have. So now we have we cover the complete instruction set of the Cortex M0 Plus. This one specifically is used by GDB for some of the breakpoints. So by implementing it, we are this fixed a few bugs that we had with GDB not working correctly, like the finish commands, and that's nice. So now GDB works much better. Another cool thing we did, we added a clock cycle counting to each instruction. So now we have an approximate clock count for like clock counter that advances in each instruction, and it's an approximation. There are like especially for load and store instructions, there are like a lot of things that can affect the clock count, like the XAP, the flash cache, and we didn't get into that, so it's not completely cycle accurate simulation, but that's just the basis if we wanted to do in the future cycle accurate simulation. That's a few bugs that we found in the instructions. I think like just edge cases. And then this is just a test case for another issue that we looked into in the last episode with the return from exception that didn't, exception entry that didn't clear the LSB of PC, and that caused troubles with, I think it was trouble with EmbeddOS. Setting up ESLint was really important. It found it's just a tool that helps us find problems in the code, and it found missing breaks in exception return, which would probably lead to a bug in some situation. And this one wasn't too severe, so I think this is one of the most important things that we did in the spontaneous live streams. We implemented a GDBClient that allows us to speak to the OpenOCD that is running on the that is connected to the physical Pi Pico to the silicon, and it can also speak to our GDB server. So now we have a way to compare what happens on the real silicon versus what happens on our emulator, and then we run a bunch of tests, all of our unit tests against, we switch them to use the test. This is mass refactor. We switch the test to use this GDBClient, and then now the test can also run against the silicon, so you can verify that the tests are indeed correct. And then yeah, just a few missing functions in the assembler, so to make the test code more readable. And then I think the other interesting thing, we fixed a few bugs in the GDB client and GDB server, just making them better. But gdbdiff, I think this is the real highlight of all we did. It's based on GDB client, and it basically just runs a piece of code from the same location on both the simulator and the silicon. So we load a program into the emulator and silicon, press play, run gdbdiff, and it runs them instruction by instruction, comparing the registers, and tells us whenever there are any discrepancies, so any bugs in the implementation. And then you can see a bunch of bugs that we found. This one is, if you want, you can read the details here, but it wasn't found by gdbdiff, but you can see all those like bugs mostly with the flags, like with the carry flags and LSRS, and all of that were found using this tool. We also started implementing the RTC peripheral because we tried to get MicroPython to work. It still doesn't work, don't worry. And then after the last spontaneous live stream, Valerio kept running this GB tool. We ran it for like 400 instructions or so, and it found something like 4 or 5 bugs. And he kept running it for like, I think, 50,000 or something like that, maybe even more instructions, and he found those few more bugs, like 1, 2, 3 new bugs. So at this point, I can say that I'm much more certain that our instruction set implementation is correct. There might be some very edge casey bugs, but I think we found most of them. And Valera also improved gdbdiffs this week, like he made it possible to run it continuously. So if it finds a discrepancy between the silicon and the emulator, it just updates the registers in the emulator, and it continues to run. So that was like a 6 minute summary of what we had in those in the last 2 weeks. If you want to read more about gdbdiff, there is a new log. Let's refresh this page. It's like a week old or something. Yeah, so there is like this log that explains better about gdbdiff, and of course you can also check the live stream that we had this weekend. And back, and yeah, actually we can probably close all tabs for now. But yeah, I don't think right now. Yeah, and now once we are done with that, let me say hi to Punith, to Mash, and Steve. Good to see everybody here. Okay, so there are like 2 more issues that are like we still have to look at. One of them is there is this program, and if you set a breakpoint at main, then you see that one of the registers, specifically R12, has a different value. So on the silicon it's 5, and in the emulator it's 10. And it could be like because of I don't know where this value is coming from. It's one of the instructions that were executed prior to main, but it could be like some kind of issue with unimplemented peripheral or with the timer. I don't know. We'll look into that, but not now. We have all the details to reproduce here as soon as we want to look. And there is also something else that Valerio found. MSR doesn't update the registers in the same way in the emulator and the silicon. Again, I'm not sure if it's like a timing issue or something like that. Maybe it has to do with caching. Not sure, but either we will look into that. INTR, one of you, if you want to investigate that, then that would be cool. But today we have a few pretty big missions. We have to do the timer alarms and start looking into, I hope to start doing GPIO interrupts and also the SIO divider. So a lot of stuff to cover today. As usual, I'm optimistic, but life sometimes things prove a bit harder than I anticipate, so it might take more than this session just to get those two, maybe even this one. So yeah, let's get started. Timer alarms. Oh, and by the way, now instead of using this, where's the code? Why do I have this? Probably don't need this. Yeah. Instead of having this file, I don't know if we still have it. There was like this to-do-txt. Yeah, probably deleted it. Oh, here it is. Here it was. I probably deleted it. So instead of having this to-do file, now we have proper issues on GitHub. So that's another new thing. Cool. So timer alarms. Let's see. That's section 463. Section 4. Right. Datasheet, timer, and alarms. So the timer has 4 alarms, outputs several interrupt for each alarm. The alarm match for the lower 30 bits of 60 bits. Okay, so the alarms can fire about 72 minutes into the future. To enable an alarm, we need to enable the interrupt in the interrupt register for this alarm. We have to enable the appropriate timer interrupt in the processor. So I guess one of those 3 first interrupts, timer IRQ0 to IRQ3. And what else? Where is this? Alarms. And finally, we need to write a timer we would like to interrupt to fire to alarm 0. The current timer in timer whatever plus your desired time in microseconds, and it also sets writing the time to the alarm. Also set the armed bit as side effect, and once the alarm is fired, like once the time has passed, our armed bit will be set to 0, and then we need to write 1 to INTR to clear the interrupt. So it doesn't clear automatically, it's a latched interrupt. So once the condition is met, it's set to 1, and then we need to clear it. It has memory. Okay, so that's like how timers work. Let's take a look at the registers. So we have no, not the RDC, the timers. Yeah. So we have those timer high, low, timer probably, yeah, write and reading. So I think we already implemented them. Let's take a look at the code. So I don't think we need MicroPython. I built it with debugging simples, but I don't think we'll get to look into it today. So let's close this. Pico SDK, we might need it, and examples. Okay, cool. So let me see. So we have this timer, and right now we have this Raspberry Pi timer, which has those registers, and yeah, I think one thing we probably want to do and we have a file for SysTick, or no, we probably implemented SysTick in the RP2040. So I think we started working on it at some point. Let me see. We have SysTick. Not sure it's complete, but yeah, there is this like clock abstraction that knows how to pause the time when the when the emulation is paused, like when you pause it with GDB, so timers don't keep running while you pause on GDP. And I think one of the things we probably want to do is, instead of in this like timer implementation right now, we just call get current microseconds instead of using this clock. So now we are also going to add alarms. So I think it would make a lot of sense to, instead of like sort of implement our own clock logic here again, just use this clock. So let's do constructor private clock. Yes, we have this clock, and then it's also read only. And then we need to call super with, we need to give it the RP2040 and name. Yeah, I guess we can probably get a clock from the RP2040. Then this clock equals RP2040.clock. Private clock. All right. One can also be private. Okay. Nikari asked if we implemented micropattern. No, we haven't. We looked into it in the last stream, and we just got forward a little bit, so it still gets stuck in some at some place in the initialization code, and we didn't have debugging symbol, so we didn't go into that. But yeah, once we get the timers and the GPIO, like once we get everything that we need for the Pi Pico div type course that I have tomorrow and on the next few weeks, then I would love to take another look at the MicroPython, or maybe we'll do a spontaneous live stream for that if you really can't wait. Anyway, so now instead of reading from this function, we can just read from this .clock.micros. We need microseconds, right? I think we do need, yeah, that was microseconds. Yeah. So yeah, now we still have the same timer, but it's based on the clock. And one of the cool things of using this clock is then we can also create a mock implementation of this clock for testing. So we can like move the clock forward and, you know, use a mock clock for the unit tests just to test the logic here. Anyways, so so now this uses the clock that we implemented for SysTick, and we need, let's see, so we have those registers to HR and LR are reading from this time register, and row H, row L are reading, and there is like this implementation of writing to the time, but we'll get it after the alarms probably. Don't think it's very important. And then we have the alarm, and whenever we have 4 registers, and writing to each of them will just arm that alarm and configure the time it will fire. So I guess we need another class to store the state of each alarm. RP timer alarm, and that it could be armed, whether it's armed or not, and yeah, target time, and maybe target micros. How many microseconds? When will this alarm fire? And yeah, probably need some more stuff, but let's do private read-only alarms. It's just we have RP timer alarm, and let's also add like a name. And this name is just so it's there to debug if we need private read only name string, then the alarm, it starts from 0. Okay, read only name. right? And then we can say that armed is false by default and target macros is 0. And then so when we try to write to one of those alarms, these need the registers as well. So const alarm 0 is 10, right? 10, 1, 2, 3, 14, 18, C, right? C. So whenever we write to one of those, we need to set a time for the alarm. So is 1, 3, 3. Maybe you also have like the raw value of this alarm. So value just yeah, I'm not sure if we need it. If we'll need it, we'll add it. Just because we want to be able to read it back later. So we can do something like that actually. Instead of repeating the same code, alarm index, because we know they are like spaced by 4, like that. Take the offset minus alarm 0 divided by 4. Then alarm is alarms at alarm index, and then alarm armed is true because whenever we write to this, it arms the alarm, and alarm dot target macros equals value, right? And doesn't like the fact we defined the variables inside a const case, so we need curly braces. All right, and then let's also support reading those values back. Just turn these dot alarms that sequential number dot target macros. Cool. So we have this, and now we need to be able to say return the armed value. So it's write clear. So it means whenever we write to this register, it clears the bits. Whenever we write one to some position, it clears that bits, and reading from it will just yeah, it says write to corresponding arms the alarm automatically, but writing once here will disarm the alarm immediately without waiting it to fire. Okay, so let's implement this armed register. U20 offset. So when we are reading from arm, we want to say this dot alarms. Actually, yeah, we need to we already all have constants for those shifts, so there's something like this. We just need to build this bitwise value from value of alarms. If it's armed, then 0, otherwise 0, and we can be this time and 4 sequential number here, right? And just add another set of parentheses, and this should basically the colon, and here we also want numbers. Yeah. Okay, so that should basically read from armed, and then Tomasz is asking how I generated like the sequential numbers. It's a plugin for Visual Studio Code. I think it's called, let's see. Yeah, it's probably sequence generator. Oh, vscode-input-sequence. So it's really handy if you need to generate like sequences of numbers. I really love this. There is also another very cool plugin. Let's say for some reason I wanted to add 5 and multiply the result in 25, so I can do this, and then there is like this cool plugin, calculate and replace, and it would just write the result. So this is also super useful, and I think this one is called calculate. Yeah, that's the name of that extension. So super useful, I think so. Thanks for asking, Tomasz. All right, so actually I want to start writing some test cases for this timer because we still don't have any test cases. So here, yeah, so let's add this timer.spec.s and then describe timer or RP timer. Then let's create const should, or maybe describe alarm. Then should set alarm armed when writing to alarm. Let's test it with alarm one register. So yeah, we should const RP2040 new RP2040 because we need one for timer, and then timer is new RP timer with RP2040 void timer, and then we can say something like timer write unit 32, or maybe we can yeah, we can just unit test it for now. Eventually it would be cool to have some assembly compiler, so maybe use our small assembler or even build a better compiler and write small assembly test programs to test the timers, and then we can also run those programs against the physical hardware and test that they work the same like we did with the instruction set. But for now, let's go with this simple offset, and then we are writing 1000, and then we expect timer.rein. Let's call this as well. And this is something that I usually don't like doing, you know, copying values from the test code, from the actual code to the test code, because then there is a risk that I copy a mistake. So please double check me now if those values are correct. So we expect armed to equal, then it should be, let's see, alarm 1, so it should be the second bit, it should be 2. And this didn't work. Why is that? Bug here already? I mean, value, it says 3, so it's like alarm 0 is also armed for some reason. Interesting. Arms. No, I'm happy you like the extensions, Dario. So yeah, so oh yeah. This is a stupid bug. It should be otherwise 0 bitwise or with this value. And now the test passes and found this stupid bug. Thank you, test. Set 1 to armed when writing alarm 1 register. Okay, and then it should disarm alarm 2 when writing 4, that's corresponding bit, to the armed register. So that's the write on clear behavior. So we have this alarm 2 as well. First of all, we are arming the alarm, and then each wall 4, and then we are going to write armed this value. Just write ff to clear all the bits, and then we expect armed to equal to 0, which didn't happen now, but yeah, I will implement that. So case armed value armed 0 0 armed equals false. And we could have probably done this with a for loop, but I don't know. Hard to tell which one is better in this case. One. This. I mean, we have this plugin that sort of does this for loop for us, so I don't know. Cool. And then we have this behavior as well. So now we can set alarms, we can arm them, and there are like also those interrupts. So basically we have those INTR register and INT-E register and INT-F register and INT-S register. So let's see. So this is read only, it just returns the interrupt status after masking and forcing. This is read write, lets us write and force interrupts. This is like to set which interrupts are enabled, and this the row interrupts before like enabling or forcing them. So that's the and this is also write clear. So let's implement all those like registers. Private E F. What else did we have? Int R, which is row. Maybe let's give them better name. Enable, int force, and they are all 0, I think, at boot, right? Yeah. Doesn't have a value 0 and 0. 0. Okay, yeah. And int status is actually calculated, so we don't need to store it. And now we can implement reading and writing from those registers. So probably create, let's first write it and then think about the test cases. So writing to int E, just update, have these register values, so it will be easier to copy it from here. Right. Yeah. So all of those, and then we can say if also names case most of them don't need int s for writing because only register. So yeah, so when we read turn this row is enable, yeah, and the force and return. Oh, this is actually a calculated value. It says where is int s ints interrupt status after masking and forcing. So we take the row interrupts, we bitwise end them with not sure which happens, which takes priority, if it's masking or forcing, but basically it's bitwise end with the mask, the enable, and then bitwise or with any about force. I think sure if force takes like one wins. All right, let's just zoom for now. I'm not sure even if this forcing interrupts is actually used in the wild, but if you can find any information whether force overrides the enable or vice versa, then that would be useful. So we are taking row, and yeah, let's assume that force only takes place when the interrupts are enabled. So this or force, then bitwise and with enable. So we have those reading, and then for writing we can say this dot. So this is actually I think where is it? This is right. Huh? We are not in the correct place. Sure. Yeah, these are right clear. So we need to say this INTR row take value and basically clear those bits, but we don't want all the bits, just like, you know, these not, and then we just want the lowest bits because only 4 bits that cleared. Actually, this doesn't really matter, I guess. Yeah, because this is supposed to be 0 anyway. So I guess we can just clear all the bits. All right, break, of course. Thank you, Islint. This value here we can only take relevant bits because the aren't defined, and this dot enforce thing. And I think we got a basic mechanism. The only thing that we are missing now is actually the thing that fires the alarm, and also like the part where it triggers an interrupt with the microcontroller itself. So let's see. So we have like code here. Do we have any other registers we need to implement? Let's take a look again at the list of registers. We have decided not to implement writing right now. Reading, we have them. Alarms, we have them. Those don't have those. Also pause poses the timer. Bug pause is probably not interesting. And pause, you know, already here, so let's have the code for it. We should have a different clock for timer because it can be paused independently of other clocks. And that's Boolean, right? Private pause, probably false on reset. Yeah, false. Then pause and pause on, otherwise 0. And then let's writing to it. Pause 2 and 1, and convert this to Boolean and break, of course. And then to actually pause timer. All right. So now we need to enable to actually fire those alarms, and thinking we should probably take a look at the clock. We have like those method to create a timer that will be invoked at some point in the future. So probably have this method here, a timer. Call it whenever we update an alarm. So each alarm should timer is that clock timer. Now, if armed, then yeah, we need to figure out now, and then we need, so when writing to alarm, we can say alarm.timer is clock a timer. Then we need delta, which will be a moment, and fire alarm. Fire this alarm. This method in a moment. Let's now focus on the file. And we can say delta just tell you minus how much time we have to just take the micros clock, and we only want it to be we want it to wrap around. So if like micros is f, and so we basically only want the lower 32 bits of this, but we want it to be assigned always. So I think this will do the trick. Let's this alarm and timer, so that's the difference. Yeah. That should probably be another test. Okay, so now we have the delta, and we can create a timer. And one thing we also need to do, if alarm.timer, then already had a timer, then schedule it, cancel it. I think. Oh, delete timer. So timer this clock timer and alarm.timer. Cool. And then we have to implement fire alarm, and we'll do it in a moment. But first, let's so whenever we disarm utility method, disarm alarm, alarm, have a time ARP timer. Armed false, alarm timer, then clock timer, alarm timer, and then also now want to be used. Here we can alarm, so during the timer as well. Disarm alarm, and here we can also do it just before arming it again. Disarm alarm. After the timer, I think it's pretty much all that we have to do, right? I mean, these are the only variables they affect alarms. These ones affect interrupt. So let's do this fire alarm method. Private fire alarm index number. That's an index. Yeah, that's used. So const alarm set index. So first of all, we are going to disarm it as soon as it fires, right? I think that's what the datasheet. Timer, alarms. Armed and don't need the timer anymore. Arm it as fars, and then this dot intro. So we should raise the interrupt flag. Just yeah. It will. Yeah, maybe we'll something like this. Value. Yeah. That didn't work. Expected. Yeah. All right. Number. Then instead of like constant, with the bit value, so reduce the chance for errors, and also do. We are reading armed. So yeah, we can. Actually, we can. Now we can do it with a for loop very easily. Once alarms and value bit value, then shorter code, and it file. What did we do here? All right, still green, perfect. We had another place. Bit value, so right, 0. Cool. So armed. So when we fire it, we update the interrupts, and then I think after updating the interrupts, we just want interrupts, and this will just check if we need to actually fire an interrupt with a microcontroller. So we are also going to do it here whenever we update the interrupts. Sure. Yeah, I think we need to even when we clear the interrupt. So yeah, so let's implement interrupts, and then for alarms, or in this case I think we'll need the index, because the index is also the or maybe we can just, you know, add an IRQ number as well. Only IRQ number. Make the code a bit prettier. Yeah, it just happens that the IRQ number is also the index, but yeah, it's still prettier this way. So for const alarm of alarms, and then first of all, yeah. Oh, actually, yeah, I think we can just use this value of int status to see if we need to fire any interrupts. We already have this logic like here, so to remove this and add a getter instead, and only in status, and it will be this, and then need to do, so yeah, probably move this IRQ number, because we at this point we are no longer really working with alarm objects, just with interrupts. So for 0 I4 some alarms or alarms lengths I plus, and then let's read const in status state this, yeah, just read it, and then we just want to update interrupt, and that's the IRQ, and then if in status and if this bit is enabled, yeah, we just want to convert it to boolean, and now we just need to implement an parentheses, and it does pause. Oh, getter, yeah, a getter. Now it's not anymore. And now at this point we want to create this update interrupt method. So it will we will use it from the peripherals to either fire or clear interrupt. So where is this code? There is so much code here to start refactoring it. Anyway, there is like a check interrupt, check exception, whatever. Yeah, check for interrupt. So here, IRQ and value, and then we need to see if value and these dot pending interrupts, and it's like not set. Then there is a new interrupt. Then we need to it's not pending yet. Then this dot interrupts IRQ bit constant, so code will be a bit more readable. Qubit, and then we also need this dot. There is like a variable that tells us to check for exceptions. So if interrupts updated, it's true. So on the next instruction, we'll execute the interrupt handler if we need. Else, if value is false and it is 1. Actually, I think if it's false, we can just clear the bit, and we don't really care. We don't need to say interrupts updated, because if we clear this bit, there is no reason to check for pending interrupts. I mean, if we already have it true, then it will stay true, but we haven't changed anything that will need to check for new interrupts. I mean, we haven't enabled any new interrupt. All right, so we have update interrupt, or I have better name for it. I'm not sure. Naming is hard. If you have a better name, let me know. Rather than update maybe set interrupt. Yeah, let's call it set interrupt. Cool. So I think at this point we have this mechanism set in place where whenever an alarm fires or somebody changes those interrupt registers, we are just updating. We are updating those registers, then reading the updated interrupt status and updating the microcontroller. So I think that should be good. But you know, we can't know until we have a test case. So let's try to write a test case for this. And yeah, so the test case would be, it should generate an interrupt when RQ3 interrupt when alarm3 fires. Just keep our convention of writing the test code on the left side of the screen. So let's see. So first of all, we are creating this, and now we should timer.writeUnit32, and we are telling it to fire in 1000 microseconds. Pre-register, well, right, and then this arms the alarm, and now we need somehow to move the time forward. So for that, we are actually going to replace the clock with a mock implementation, as I said before. So yeah, so let's change this to an interface iClock, and the clock has like, this will be like one of the clock implementations, and the clock will have like pause, resume, methods, interface, micros, getter, and number. Those, I mean, not implement, just declare them. Doesn't return anything, and turns clock timer. No, it's already also using like time API. So let's interface timer. Know if we actually need. Yeah, it probably has pause and resume, and then rest is. Yeah, typing is sometimes challenging. Yeah, and then delete timer. This. Right. So we have this interface, and now inside the RB2040, instead of clock, yeah, say that clock is iClock. And instead of this calling it clock, let's call it real-time clock, because it's like we actually refactor this to a new folder that will clocking thing. So there is like so there is real-time clock, which is just actual clock station here. Clock timer. And then there is word, and just like the interfaces, export them. Then we'll have in a moment we'll also have MockClock that we can use in the tests. This one, clock, and iClock timer. Yeah, maybe not sure how to type this correctly. Get back. Let's first of all create the abstraction and finish creating the abstraction. So yeah, maybe instead of making this clock constant, we just move it to the constructor. So whoever is calling us will be able to decide on the clock. So constructor, yeah. So by default, it's just a real-time clock, but we can override it. Clock for that. Clock. iClock timer. Timer. And this is happy because implements the clock interface, implements the iClock timer. All right. Funny. Yeah. So probably Google Assistant can also do this for you, like set the timers. It would be fun to implement this clock over Google Assistant using some text-to-speech and speech recognition. If you're feeling adventurous, then you can definitely run the emulator over time given by the Google Assistant. Anyway, so we have this real-time clock now, and I think the code is happy with it. And let's now implement this MockClock. The S and MockClock code, but adapt it. So instead of having all those methods, pause and resume don't really do anything. And there is like current time, or called it millis, I think. Millis is number or micros. And then we have this advance method, which just advances the clock amount number. Then this dot micros equals delta micro. Cool. And then creating timer will just timers here will just be a list of pending timers, and then when we advance we can call those timers. So timers is just new set, or yeah, I guess we can probably optimize it, but it's just a MockClock. Don't really care about it being efficient. So it's equals, first of all, start with micros equals 0, and then it's a new set of timers, and that would be MockClock timer. And then whenever we create a timer, we just this timers add new MockClock timer with micros, delta micros, and the callback. And yeah, let's return it. This timer equals this timer, and whenever we want to remove it, we just delete it, and don't need a getter for micros because always already a variable. And then now when we advance the timer, we just advance pending timers, this dot timers dot values, right? Or we can just array from timers, and we just want to sort them. So sort B yeah, so here we are going to only only, no logic here. You just mock timer, so it's simple. Right, and then a dot micros minus b dot micros, just sort them by the time they expire, and then while pending timers, actually there is let's do it like that. Yeah, let's actually make our life easier. It will just be instead of this will just be an array MockClock timers. Only private read only. Yeah, still for some reason. And then here we are just timers push. Then this timer sort. I think it's sorting in place. So array, of course. Sorts an array in place. Documentation. And then this is always sorted, and now we are doing file timers 0 and time this. So while there is a timer and the time on target time is micros delta micros. So while there is like any pending timers, of course, and the first time is less than or equal target time, then these timers 0 callback dot time, or we can timer this dot timers. It's the same array. Shift, just remove the first element and call the callback. And the reason I didn't want to sort it here timer is timer. Oh, it's happy. So the reason I didn't want to sort it here, it could be that in the callback we are creating a new timer, and then we want this to be reflected here. So we want this loop to run as long as something that created a timer, and that could be one of those callbacks, still like has to run before this target time. So yeah, so I think we have like did get iClock timer, and then const. Not sure if there is like array has like timer. I don't think it has like this method, but we can find the index of timer or off. Timer isn't, yeah, and then this dot timers dot splice, so index and the timer index. Later, if it's found, then just remove it. Splice just removes some element from given index. Want to one element this index. Again, it does it's mutating operation. It does the removal in place. It mutates the array, and method empty, just to keep ESLint happy, and the same here and here. Cool. All right, so, and we don't probably parameter. Yeah. So we have our mock timer implementation, and now we can actually check, test our code, and we can say that. Yeah, so instead of using the standard clock, let's const clock is new mock clock. Find why those imports aren't clock auto imports aren't working, and then we can create this with our MockClock, and then we can, doesn't have to be 1000 hexa, we can call clock.advance and 200 micros, and let's see. So at this point we expect that alarm to be armed, but after advancing we expect it to, and you can see it's no longer armed, so it has been cleared. And we also expect this expect RP2040 dot pending be false. And why is that? Because we still haven't, to be 0. There are no pending interrupts because we still haven't enabled the interrupt. So the interrupt has fired, but we still haven't enabled it. So first of all, let's see. We expect int s. Let's define it. And again, I'm going to this horrible thing of copying it values from here. So we expect the int status. So at this point it should be 0, but at this point it should be, oh no, not the int status, the row interrupt should be 0, but the row interrupt should be 8 because yeah, the interrupt should have, the bit should have been set, and then we can say the int status should be 0, and arm the alarm times time so that the alarm will fire. And now sometime in the future, at some point, we are enabling the interrupts, or the interrupt is timer for actually for alarm 3. So in this case, we are writing to int e. We are writing there. Let's say we enable all alarms, and then at this point, I want it to be 0. We want the this to be pending, like, and this is true, and also we want ints to be 8. And now we are going to do one last thing and clear this interrupt. So clear the alarms interrupt by writing to this int status or int row interrupt register. Yeah, R is 8, and it shouldn't have changed. Let's just clear this specific one. So we are going to write 8. And now at this point, we expect the interrupt status to be 0 and also pending interrupt to be 0. And we can also just, to make sure, RP2040 dot pending interrupts, or no, interrupts updated. Well, true. Yeah, interrupts were updated. So yeah, so we have this test case now with the mock clock, and it seems pretty good. I mean, it seems like the test passes, which is pretty good. And yeah, we haven't used forced interrupt. Yeah, I'm not sure we should spend time checking, so we can remove it. And you can see we have pretty good coverage of, not amazing coverage, like all those getters aren't covered, but at least like the basic flow of setting an alarm, firing an alarm, and doing the interrupt thing seems to work. Hey Jim, good to see you here. And I think that's a good time start like trying and running some kind of code that would test it, because we have the test case and it passes. and the files just cleaning. And if we go to the Pico examples repo, is that on? Let's see. Not in the WSL. We open it in WSL. Pico examples. So we have there is like a bunch of examples for the timers, and one of them is doing, I think, timer low level is taking advantage of you can see it's sending an alarm, and then it prints whenever the alarm fires, and the alarm is configured to fire IRQ every says every 2 seconds. Yeah, so let's try and see how this goes in the emulator. So it's the build timer low level cp timer low level elf start to mnt cp-up2040.js. Now let's try to run it in our emulator files, the ones that are ignored, and that's our low level. And as usual, we're going to be optimistic and then get slapped in the face. So we are going to just npm start and hope it to print alarm fired every 2 seconds. What did it say? Timer low level. So we got a first print and then nothing happened. Not too bad. At least the first print went pretty good. It prints here timer low level, but then there is like this busy wait that just waits for alarms, and everything works well. It should fire, but we probably missed something. So this is time to start debugging, and let's add some debug prints here. See if the alarms are set. So console predict. Console log alarm index armed, and then also add a console log in fire alarm fires, and that should give us pretty good idea where things don't work. So yeah, we can see that the alarm armed, but it never, oh, it fired. So it armed, it fired about 2 seconds later, but it never printed this message alarm IRQ fired. So yeah, our printing, we didn't get the UART. So at this point we should probably check what's going inside. Check interrupt, set interrupt, and let's do console log after set interrupts is dot pending interrupts. Yeah, and alarm 0 armed. Yeah, it fired, but despite the fact it fired, we have all the interrupts, like it says pending interrupts are 0. So let's also print the value, see if the IRQ and for all the IRQs it should be 0 because they shouldn't fire except for the first one. Yeah, alarm 0 armed. Yeah, for some reason it's called with false. Let's see why. Timer false it with false. Console log status. Let's also print the enable and the INTR this intro. Right. And waiting 2 seconds. Yes. So we can see row interrupts are 1, but int enable is 0. Interesting. It seems like nobody enabled the interrupt. And I'm already seeing the problem. You see, this enable register is at 38, and there is an atomic write that we haven't implemented. So the thing we are going to do right now is implement this atomic writes. We have this small tech debt, and that's why it didn't work, because it doesn't do a normal write, it does an atomic write. So instead of blurbing about this unimplemented, let's implement atomic writes. Bugs are we already know what's the problem. So how do we go about atomic writes? I think what we can probably do is add another method to the peripheral. The atomic write uint32 offset value and write type, and then const type. There are like 3: set, clear, and XOR. So check how they are working here. Or remember, there was like this section, the atomic writes. Sorry, register access. So XOR set clear. Atomic XOR 1, then 2, and clear is 3. So write type anything, and we'll just have this default implementation atomic write uint offset number write type. Then so do something like that. Current value is reading it, then switch write type. Maybe we can write, could be just a function. Atomic update current value number write type number new value number, then switch write type. So if it's just atomic XOR, then current value new value atomic set, then we are returning current value or new value, and if clear, we are just clearing those bits. Otherwise it shouldn't happen. Value born atomic update called with invalid write type. All right, now we can use this method, and we can say this dot write 2 at offset value, and const value is just atomic write old value write type and the new value. Atomic update. Yeah. Okay. And then this will just be like the default implementation, and maybe we can just atomic write 30. Yeah. and then we will change the RP2040 to call this method if like, so this will never happen, like this offset will never be more than 1000 hexa. Implement instead of writing referral.write. Yeah, so atomic up, and then so it take those bits that determine the atomic write and give them by 12. Offset is just address actual offset bits, those bits, and then if atomic up, then our peripheral.atomic write offset value, otherwise it's just a normal write that value. Oh, and there is like the atomic that let's write, or maybe atomic type, better name for it. And atomic type. Okay, cool. So we have this default implementation, and I think for most part, like it should just work for most peripherals. They shouldn't really care about it as long as they implement reading and writing. Maybe in some peripherals we'll need to override it. Let's see. Here. Yeah. Probably updated. Yeah. Atomic write. Atomic. Right. Atomic 2. Happy, but some tests are failing. Which one? Yeah. So yeah, we have like this should support atomic IO register write addresses, but now it actually does atomic writes. Test. Peripheral, and in this case we will call, let's say that read. So this is 1 the offset, so it will be XOR, and we want read to turn function turns a, that's like the current value, let's say turn ff, then we are XORing it, we are writing 0f, then we expect write to be eventually called with actually also checking. Let's do new logging peripheral and RP2040 atomic right, and then mock tab. Don't remember the status for tabbing a function. Spy on, yeah, spy on. So we are going to spy on. Let's peripheral. So we are going to spy on peripheral dot write uint32, also on the read uint32. So calling to read uint32 will turn mock value. That's the old value, and then mock write spy, and then say peripheral, and calling write uint32. We expect this called with so we are XORing with F0, so here so called with we do atomic. Oh no, that's fine. So we should call the atomic this test. Oh, you just affects it right interface in all of the other tests. So quick. Okay, now it's here. So focus on this test all the way here. What happens here? So for some reason, atomic type. See? Oh yeah, of course. Need to be the correct bits. Now probably yeah, it entered now. It went in atomic right, and then yeah, and then atomic right. XOR update offset should be like 120, but for some reason it's FFFF, so probably have a bug some. Oh yeah, be bitwise and logical and now it's green. So yeah, so it's good that we have this test case and that we now fixed it, and we know that our atomic right, at least for XOR, it probably works well. In set and clear, okay, we can probably skip testing that, but thanks God we created this test in the past. Okay, so let's try to run this one more time and see if now the alarm works. Yeah, yes, almost good. You can see that it fires, but for some reason then so that's great, like it fires, this works, but for some reason it keeps firing forever, and I wonder why. I mean, as soon as it fires, then I think the code here, see when the IRQ, it should clear this alarm by writing to INTR. Probably doesn't do it. Is this read from an invalid memory address, which may have something to do with it? No. 00. What's this 00? Familiar to me. Yeah, it's probably one of implement already, because always clutter our logs. Anyway, so yeah, alarm IRQ fired. Yeah, so something doesn't clear the interrupt probably. Let's see. INTR timer, that's tick R timer S R, so intro, writing to intro, clear it. So let's console log write to INTR value to in, just to see row, and then in check interrupts we should update the interrupt handlers, like the pending interrupts. And what happens here? Write to INTR 0. I don't think they are writing 0 here. Pretty sure they aren't writing 0. Like it should write 1. Double clear bits. HW clear bits. Here we have a problem. Understanding of the datasheet. Maybe this INTR is not right clear as I thought. Are you up? Says WC, so I think WC means write one to clear it. Isn't it the case? Or is it just a toilet? Probably explanation here of this single bit is typically set, written by the processor. The bit is cleared by writing one or clear alias. Also a way to clear. So maybe they are just, you know, writing one. HW bits. Okay. Just print this. I think it's just a thing where WC bits writing to a WC value should probably like yeah, this is an atomic write, then we should update here. Should say clear area. For writing one here should also like, so yeah, so can probably atomic write would be write the new value with 0. Maybe we can just add whether it is atomic write or not to the base. Boolean. Yeah, atomic Boolean and atomic will right, then anything, then here true because the atomic write is happy, and here we are writing the false because it's not an atomic write. Here finally not an atomic write. Yeah, I'm starting to think, yeah, maybe instead of atomic write we'll just have write doing 32 row just to get the atomic write, atomic type, and it will always like fall, will always take care of writing. Maybe we'll put it right here in 32 atomic. Then we can also do this right here in 16. Would be atomic 12 atomic. Then we have here set an atomic type. So address that type and same goes in right here 16. So offset atomic type. So we want these writes also to support like this type of these narrow writes also to support atomic writes. And then side peripheral we can have in 32 atomic, and then just another case, so case atomic, other one normal, then it just returns the const atomic normal. And then yeah. Finding the right interfaces. Don't want this atomic or yeah, and then just yes, you can say clear. So just to check if this is atomic clear. Because that should be the spatial case for WC or write clear boolean. Then if atomic clear atomic, clear, otherwise we don't care. And then we can say atomic clear if atomic type just equals atomic clear. Okay, now finally about interface clear, and here false, it's clear, it's store, here it's happy atomic now, right, happy. Finally here now we need to pass this down boolean, so we need to update all the peripherals. Maybe there is, yeah, I think there is probably a better way to do it. Having to keep track of this value, we can just I don't like it really, but probably simplify the interface by just flag the instance. So extra parameter, we can protected atomic clear is false, then this atomic clear, and this atomic clear is true if atomic write is yeah. Now probably well parameter to worry about. Here we don't. Good. The timer, right? This is good. And then finally we can say test test. Failing. Do something bad. Test. Filter. This one. Probably messed up something here. Doesn't call right unit. Oh yeah, this is just a dummy peripheral. Probably. Just like here, use a real peripheral. So, IT2. Complete. Test peripheral. Okay, now it's green because we have this peripheral that implements the atomic write correctly. And do the same here. And this also be green. And yes, tests are happening again. Peripheral. Here test instead of dummy peripheral. Okay, so finally, I think we fix this mess with the atomic writes, and we won't have to worry about them too soon. Yeah, and then yeah. Okay, so yeah, I'm thinking we can probably do something even. So write clear is probably something that is going to repeat a lot. So instead of having this atomic clear, we can probably have write clear bits and then write clear bits 0. And now we are doing write clear bits. Just print them here so we don't need to worry. So if it's atomic clear, then this is value. Or we can just say that write clear bits is just call it row write value. So it's the value without all those atomic update. And then for write clear bits, we'll just use this value. So it doesn't matter whether you write it to the normal location or to the clear location. It will just get a row value and clear those bits. Whew. Yeah, that was long. Figuring out the correct way to do it. And now instead of looking at value, we are just look at the row bit value here. It's write clear, and same goes. Test will need to call this write atomic method. So row write value, and same goes here, like this one. Also write clear. So whenever we have a write clear, we have to look at the row write value instead of like this value which. And there might be a better way to architect this. So if you have an idea how to re-architect this better, then I'm open to refactor this. But for now, I think this will do the trick. Let's just test timer spec TS. In this case, we're to atomic. Just going to normal, or you know what? Probably do it just, we don't have to worry about it, just for the microprocessor interface. So actually going to mimic the real thing. So all right, 32, and then let's just add all these registers. Timer base, where's the timer? Timer, what's the timer? It's here. Just adding this value to all of those. Cool. Now instead of timer, that's RP2040, just for the microprocessor code. Not happy about it. Then out why in a moment. Yeah, but oh yeah, sure. Should be RP2040.32 40 and lots of greens. I like it like that. And we actually oh cool. In this case we don't even need to create an instance of the timer because the RP2040 already has the timer built in. So it's not a unit test anymore. It's more like sort of integration tests, but since we have this cool MockClock, we can actually test it in emulated I don't know how to call it, but anyway, in an environment where we control the clock. Anyways, let's do one more thing to clear the alarms interrupt like we do here. We'll do it like the real hardware. Instead of writing to INTR, we'll write to INTR clear, which has this this is the atomic write alias, and it still passes, so it's probably, or maybe will readable this way, R or yep. Okay, so now we have this test case that uses this alias, so it probably mean that this code will also run. Let's see what happens now. Those UART reads, I know why they happen, but yeah, I know why they happen, and we'll fix it in a moment. But anyway, you can see that now it fires the alarm roughly every 2 seconds. So this is pretty cool. I think it works. So those reads are happening because the way we implemented our peripheral, our atomic UN32 write. We don't really need this atomic update if atomic type is 0. So we can do if atomic type. So if there is atomic type, then this, otherwise just value. Don't need to read. Just set. Then in atomic update, we can remove this atomic normal. Maybe we can just do it like it's not an atomic normal, then we need to do this update, otherwise not. Now if we run it, we should not see this implemented, and yeah, it works. We have alarms. Hey, yeah, hooray, so much fun. And yeah, let's commit this amazing piece of work. So what do we have here? First of all, we don't want to file, and as usual, I will just run it to see that hello UART still works. Yeah, AB hello UART, cool. And the changes real quick. So yeah, we updated the tests, actually test atomic IO writes, and changed those tests to use in the implementation of the peripheral instead of like. And I think actually I'm thinking maybe this logging peripheral should just be a base peripheral, because pretty much it's sort of a base class for, let's call it base peripheral, and then all the other classes already extended. Good idea. Base peripheral. Refactoring. Happy because it's peripheral. And maybe this should will make it an abstract class in the future. Actually, no, because for now, at least for now, we are using it all here. Like, I think 40 where we have unimplemented peripheral that extends it. So we can probably make it abstract at some point and create another test peripheral for the test. Not sure. Anyway, worry about it too much right now. Okay, so we have those tests that are now using the peripheral implementation instead of like mocking it. And I this change just range space here. Okay. Then here like this clock thingy where we can override the clock to our liking. SetInterrupt we added and it works. Clock, the MockClock test, the real-time clock, which is the implementation that so far. Now we updated the peripherals. Right. Last name change. And some tests for the timers and the new timer implementation. Good, I guess. It runs the basic test, this basic thing. That one with the timers. And there are like a few more examples. Probably try to run, but they are using higher level SDK functions. Timer what? Probably uses some other SDK functions. It will be fun to try them, but console logs here. Oh, we do have some stray console log. Don't want to copy that. Okay, and we also miss this pause. Warn. Pause. We'll at least know that we have a problem here. Cool. And finally, just like base class. Okay, feed. Timer, right? Timer. Add alarms. Then thanks, Jim, for cheering from the audience. Okay, and this is your number. That's 19. Alarms, and it also meant all it atomic rights register access. This that well else yeah and add setInterrupt, right? Interrupts cool. These were up to 40. Fire dispatch, fire interrupts, and we also testing factor named logging file base. Yeah, I think that's a quite good summary of what we did past 2 hours. pretty much, and we can also close issue 19. Commented it. Yes, another one. Yeah, and now when this session finishes, I'm going to update doc.walkway.com parts Pi Pico. So we have this like list of features, and I'm going to add a checkmark here. We have the alarm, so we can say this is implemented. We still don't have pause, but I don't end like writing, so it's not 100%, but I'm already like I'm already feeling good enough with the implementation to put here a check mark. It's great. Okay, so I think we can probably start working on GPIO now. Obviously, we are not going to finish this pretty long, but we need to start at some point. We are not going to finish it this week, but let's at least get started. Before doing that, I think this is a good opportunity to release minor version, because we added a really cool new feature, probably with some bugs. npxp, probably with some bugs, but still. And while it's doing praying second, yeah, stray file, right. Okay, while it's preparing for the release, let's see what we have here on this GPIO. So GPIO is actually split across multiple places. We have this SAO, and there is like those registers that control the status of GPIO, and then there is like other registers that control the GPIO, like this function select that selects a function for each GPIO pin. Then there are like those pad registers as well. So there is a lot of work to do here to implement GPIO properly, but we added this clock, this MockClock, and this peripheral timer. Correct. This is a minor version because we have a shiny new feature. Actually, two atomic register. Other cool features that we have now. So yes, so we have bunch of registers. So there is like a control and status register for pin, and it has information. Yeah, so I think for GPIO we are going to have like a class that describes the state of a pin, and the state could be whether it's an output pin, an input pin, like it's mode, output mode, input mode, and, you know, if it has a pull up enabled or not. And then instead of like doing this, we have this funny code here which says GPIOPin set to high and to low, and it just hooks to the SAO. Then we can probably have some SAO class that will implement all those like GPIO pins, and then we'll have like those GPIO this GPIO interface that the code will be able to attach to a single pin and just listen to the state instead of like printing this GPIO is set to high or low. So let's take a moment to finish before hoping it's not running the tests against the actual. Oh, it does. Yeah. So yeah, let's restart this release. There is like this environment variable that tells it to run all the tests against the physical Pi Pico, and that takes a lot of time. Click on. Let's rerun this release. And so we are going to create this class that will have the state of a single GPIO pin, and then we'll have another class that will take care of all those SIO things like the GPIO writes and all of that stuff, instead of having this strange if statement that does this for us. So let's just run the result again. And then we also have to, oh, does that again? Comes. Strange. Oh. Strange. Maybe that process is still running, even though I closed the terminal. Otherwise, because this is not even running the tests yet, getting those messages. Yeah, now it's much faster, as you can see, and the release is going to ready in 3, 2, 1, and yeah, pushing tags, and now it will release draft and 0. We have alarms. Alarm clock here, and yeah, we also have some nice bug fix from Valerio, so thanks for that, Valerio. Another bug that he found using gdbdiff. Cool, so we have alarms, a new version, that's exciting. And now let's in a quick shift start working on the GPIO. So the first thing we want to do is just have this code that handles the SAO instead of and it's not really a peripherals, but I don't know if, but yeah, let's put it inside peripherals for now. I mean, I think in the datasheet it's still under peripherals, maybe. No, there is SSI, there isn't, not under peripherals. Yeah, I don't know, let's put it out of peripherals then. Datasheet doesn't classify it as peripheral class RP2040 or how do we call them? RP timer, right? RP timers, RP SAO, and it has write uint32 value offset number value number read uint32 offset number value number, and then we can start moving the logic from here to here. So there is like let's have it and have it refer to the constructor private read only for the RP20 instance. Right, and now we can say 40. So yeah, I see we have like this, well, maybe part, it's read hook. So yeah, so if we are writing, we can say, oh, we need to add this SAO. Only SAO is new RP SAO. This probably, yeah, auto import worked, yay, cool. And then write, then say this dot write dot SAO dot write uint32, then offset and value. Okay, and then we can move all this logic, which will be rewritten in a moment, this, and also like read part, so read uint32, the implementation, it's slash ram, this is the SAO, turn maybe we can give, like, make sure that let read hook still override else. So make sure that read hooks are still able to override SAO addresses, because otherwise they won't be able to. Yeah, do this on offset, and default it, yeah, let's add a fallback. So address offset. So now we have this like class for the SAO, and we can start handling reads and writes. So the first thing we want to do, there is like this register CPIO ID. We can remove it from here and just migrate it to SAO. So offset, and then we have case. Code is starting to look a bit brighter. See what's the offset. I think it was just 0 UID. Let's see, where is the SAO? I think it's somewhere here. SAO, by the way, if you don't remember, is just a single cycle IO. It's a set of peripherals. It has several peripherals that have fast access. So the CPU has fast access to them. CPU ID, I think it's offset 0. CPU ID 0. And then here, when we are writing, we can start working on the GPIO. So basically, there are like, right after this CPU ID, there is like all those GPU registers. So the first thing we are going to do is just take all of those GPU registers, just go here and create those instances of them. Again. Right, so cons this is a comment, and we can say this GPIO stuff, and that's the stuff that we need to do in order to add a space here, make it a bit prettier, and that's the stuff we need to do in order to implement GPIO. And you can see like we have those values, hard-coded values that are probably GPIO out set and clear. I guess this is what they do. Strange thing that we're going to remove right now. And instead of doing this, we are actually going to implement those registers. So you can see this is like very similar to the atomic write. You can there is like for the out, you can write the value of all the GPIOs. You can set them, you can clear them, and you can XOR them. So we can have a register that would yes, reading from them returns probably yeah, it doesn't say what reading from them does, but I guess for most of them it returns out set the output level for GPIO, reading back the last value written, not the input value. Yeah, so we probably have to store this value. Const GPIO value starts with probably 0. Yep. And then it's just the internal value that GPIO has in the SAO. The actual pin can be connected to different different peripherals. So we can say something like this: switch on the offset, and then if this offset is just GPIO out, is the GPIO value equals value break, and it's only 98 bits, so GPIO mask is just like yeah, just like those bits, so without those high bits. I think we have too many F's here, right? Yep, it's fine. So yeah, just setting it, and then we can set all out set case out set just as bitwise OR and GPIO out clears, and here we don't really need the mask, and there is also XOR one. All right, and then reading from them, so case, I guess all of them we can, I'm not sure, we need to check. If we want to be sure, we need to check with the silicon what they do there when you read from those other aliases, if it returns 0 or it returns the current value. Yeah, let's do that. This returns the current value. It seems likely to me that those will return 0, but to verify with silicon. Anyway, it's probably not very common to read from them, like an edge case. And yeah, we implemented all of those, and there is also like the same for GPIO out enable. So GPIO put enable is 0, and then we can just copy those for the output enable. So instead of GPIO out, it's OE. And then here it's output enable, and here it's GPIO so reading back Raspberry written right now. Set output. All right. So yeah, just we are doing the same, just with GPIO output enable. Then this is the same, verify with silicon, and we have a bunch more. So let's we still don't have a way to read the GPIO inputs, but let's have yeah, we'll implement it in a moment. And I think these are just read-only registers. It makes sense to me that those GPIO in only. And then we also have like those high GPIO, which is the QSPI GPIOs, which we have to do the same for them. So say just call them high GPIO, just like they do here. So GPIO high, maybe high GPIO or QSPI. That's the QSPI GPIO. I think that's the best name. And then we can just probably paste all of this block, a lot of copy paste, and then just here GPIO high, here high GPIO, call it like, oh, QSPI, not high, QSPI full, and same go reading. Yeah, maybe we can just move all of those together. Don't have multiple to do here, then all high, and here well GPIO high, and just QSPI GPIO. All right, we have those things that we have set, but we still need to. So this is from, we have this GPIO mask. It's horrible, constant all over the place. So yeah, and so we have this GPIO sort of basic implementation. It still doesn't really let the user interact with it in a useful way, and I think that's something we are going to probably do for the next session. So continue with GPIO. The good thing is that it shouldn't be very complicated. No, let's just more minutes. So let's just create this GPIOPin, GPIOPin.ds, and then export class GPIOPin. And a GPIOPin will have interface GPIOPinState, or enum. It's actually an enum, and it can be low, it can be high, it can be input or high Z. Maybe we'll call it input, and it can be also input with a pull up and input with a pull down. And here I'm drawing on my experience with the AVR simulator. If you check this AVR AJS, the source code, you will see that we have something really similar in the GPIO. There is like somewhere state. Yeah, it can be low, high, input, pull up. So pretty much the same. But here we also have pull down, so it can also be a state. And then for a GPIOPin, we'll have a constructor RP2040 pointing back to the RP2040, and then index maybe, right? And we'll have to figure out the for read only. And then we'll have to figure out the exact details in the next session, because I'm tired already and finish in a moment. But for now, we can just, you know, define those GPIO pins. So we can only GPIO array with new GPIO pin. So this and 0, and then all the way down to we have 98. I don't know actually 98, but I think it should be. We have 30, so from 0 to 98 more, so 5 more, I guess. Yeah, so now basically when we update read from the pin, we can so each pin has a function, and then the value of the pin really depends on the function. But for now, we can just assume that SAO controls the pin. So we can sort of implement get value, and then it just returns. First of all, we are checking if this pin is an output pin. So rp2040.sao, make this one's maybe we can do getters for them, add getters. So only GPIO value, or just GPIO, or get GPIO, and this GPIO value, and then get GPIO output, or yeah, for now we can just do them public. I mean, it would be nice to have getters, but probably refactor it later if we wanted. So rpgpio, so if output enable, check our index, this const list mask just index, and then if GPIO output enable and bit mask, probably do. If it's enabled, then turn drp2040.sao.gpio value and bitwise add bit mask. So if it's the value is true, it should be a high in state high, otherwise state.low, and then we should probably have another getter, yeah, else return rp24. Otherwise, if it's not output, then it has to be an input GPIOPinState.input, and here we need to do a count for pull up, pull down, and we'll do it in the next session when we implement the pads, where this is the peripheral that controls pull up and pull downs. And we also need to do add a way to listen for value changes, because otherwise somebody will just have to poll the values whenever there is whenever there is to see whenever there is like a change in the value. But basically, once we have those, the user can just like add a listener to whatever GPIO pin they want, and then know whenever the value changes, or read the value. And then in the next time, let's add it to do here. SAO, we also want to implement reading those. So reading those is just going to go over all the pins and read the value, and this is something the user will be able to set. So basically it's up to the user to provide the implementation of how we read pin values. So yeah, let's add it to do. So we don't need to write to them, just to read from them, because only we will have read before write, like that way in all of the other peripherals. Case in and in to implement, and this one as well. There we go. We have the start. I think we are halfway through of having usable GPIO implementation that let the users of this library attach to arbitrary GPIO pins, monitor their states, set their values, and control the simulation. And there is also interrupts that we want to implement. I think we can probably do it in the next session. I'm pretty optimistic. We had a pretty good progress today with the timer and GPIO IRQ test. That time to check out some of the implementation of the input other than blink. So just run this. Hello, see that it still runs. Yeah, runs, cool. Implementation. I think the issue number is 20. Committed. We don't have any stray console logs. Worst case, next time. Right, so to sum up today, other than reviewing what we did in the last 2 weeks in the those spontaneous unplanned sessions, we also implemented atomic writes. We implemented timer alarms, and we have more or less complete timer implementation. It's actually the first peripheral that we have a pretty complete implementation of. We also have partial implementation of UART. We would need the UART input soon if we want to get MicroPython running and usable. So I think that's something we do after finishing the GPIO. And we have at least some progress towards getting GPIO to work. And I'm really grateful that we didn't have any alarms and sirens in the session, so everything went smooth. So thanks everybody for coming and joining me today in this adventure of creating this emulator. It's starting to get a real form, and really exciting to see it working and running complex programs. And see you next week, and until then, have a great rest of the week. Bye.